Like this.
Good afternoon, Prof. and fellow classmates. I'm Gordon and this is Clarence, and today we'll be showing and telling about the grid algorithm. Right, so firstly, what is greedy algorithm? It's an algorithm that follows the problem-solving heuristics of making the locally optimal blah blah. But simply put, it's just always making the choice that seems to be best at that moment, and at that moment is highlighted because it's the important aspect of the greedy algorithm. So what are some applications or real-life examples of the algorithm? So the one we are more familiar with would be the TSP, traveling salesman problem, and the other two is money change problem and the fractional knapsack problem. And since we are all really familiar about what TSP is about, we'll just briefly go through what is TSP and focus more on money change and the fractional knapsack problem. So TSP is, let's say we have a goal, we have 4 points, and our goal is to start at point A and end at point A in the shortest distance, but there are rules implied, which is we have to visit each point once and only once, and we cannot pass through visited paths or points. So if you're at point A, the next shortest path will be considered if it's 20 or 30 to point B, and we'll move to point B, and next decision will be from point C to point C or point D, and the distance to be considered is either 30 or 34, and we move to point C, and then because all of the points are already been visited, the last point is point D, and lastly return to point A. So this is basically what the TSP is all about using the greedy algorithm, meaning the grid part is that we are choosing the shortest distance in this TSP. And now I pass on to Clarence to talk about the money change problem.
Okay, thank you, Gordon. So I'll be talking about the money change problem. So if given a scenario such that when, for example, we have two personas here, Wei Ming and Carson. So let's say Carson is actually, he just visited a restaurant and he only has $1,000 bill. So actually, Wei Ming is like the waiter, and then he needs to return the change for Carson. So yeah, this is what Wei Ming might think. He thinks that he's like Henry Golding, some crazy rich Asian. So yes, I shall do a small demo. So using just now that scenario, if Carson pays $1,000 and the bill of the meal costs 96. So based on this algorithm, it will return a change of $904, and it will be split according to the results, which is $900 and so on and so forth. So this is actually quite dynamic. But however, a greedy algorithm does not solve all kinds of problems actually. Okay, so for my codes, it actually look like this, like what I explained just now. So based on the array, it's sorted based on the descending value of like 150, 10, 5, 2, and $1 bills, and then it will compare with the main result, and then it will just deduct until it reaches a value where it cannot be detected by the next value. Yeah. So does anyone have any idea what is the best way to solve this money change problem actually, in fact? Anybody? Wei Ming, Carson? Okay, actually the best way to solve this is actually not any algorithm, but it's actually like so simple. Just use the Visa PayWave. Okay, so jokes aside, so actually greedy algorithm will, like what Gordon said just now, it will look at the best value, best decision making at that point of time. So for example, like from 5, it will choose this is the optimal solution. It will get 5 plus 7 and plus 9 to get the max value. However, if you use greedy algorithm, it will get the next value of 5, 8, and 4. So actually, like what I said earlier, greed is not always good. Next, I shall pass on to Gordon.
So for the last example would be fractional knapsack problem, and so let's say the scenario is kind of similar to the one before. We have now Randy, who decides to rob a bank which has 3 items. So one is the ring, one is a squattle necklace, and the last one is a gold bar. Right, and to him, size does not matter, and what's important is how much the item is worth. And then he's carrying a bag or a knapsack that is a capacity of 50 grams. So his goal is to fit in all these items into his knapsack and get the best possible value out of it, right? So what kind of decision making will come in place? So that's when we bring in this kind of fractional knapsack problem. Fractional meaning that you can split the items into fractions, meaning you don't have to be a whole. For example, the gold bar, you can get like half or 2/3 of it, depending on what kind of value, what's the best optimal value at the end. So bring to the demo. Just a very quick demo. Earlier we have the knapsack capacity of 50 grams. And then the weight of the ring is 10 grams with a value of 60. And then the weight of the squattle necklace was 20 and $100. And the gold bar is 30 grams at value of $120. So when we calculate the knapsack problem, we found that the most optimal value it returns is $440. So we get one whole item of the ring, one whole item of the necklace, and 2/3 of the gold bar. So that's the most optimal value. So how does this algorithm work? Is firstly we calculate the ratio for each item, which we take the value divided by the weight. So in this case, we see that 6, the ring is ratio of 6, 5, and 4 respectively. And then next we have to sort the items based on the ratio, which is already sorted from descending order, means 6 first, 5, and 4. So we add it into the array list of items. And then we add this item into the array list of the knapsack, in the capacity of 50 grams. So let's say the first item we add is the highest ratio 6, and the capacity of the bag is 50 grams. So the very first item we add is the ring, and then you deduct the capacity by 10 grams. So you get 40 grams available, and then the value of the knapsack now 60. Then next, you add the next, because we can add a squattle necklace as a whole, so we add in a 20 grams. Then lastly, we have 20 grams left, but we cannot add the whole gold bar in because it's 30 grams. So we take a fraction of it, so it's 2/3 of it, and you get $80 added to 160. You get $40. That's the most optimal value you can get from this, from robbing the jewelry shop. Right. So in terms of complexity, the first part is we sort the array list in terms of the ratio, right? So 654. So as earlier mentioned in class just now, the complexity of sorting is similar to a quicksort kind of algorithm, and its complexity is O of n log n, right? And then because the if statement is inside one for loop, so the complexity is just O n. So you just n log n plus n. So the overall complexity is just O of n log n. Yeah. So with that, we have come to the end of our presentation.